Today we're going to prove the famous Gauss's Theorema Egregium. It states that on any regular surface, two-dimensional sigma 2 embedded in R3, the Gauss curvature K depends only on its first fundamental form G. In other words, K is intrinsic for regular surfaces. Okay, so we know that the Gauss curvature is equal to the determinant of G inverse H. So if you can prove that the determinant of H is dependent only on G, then the whole thing would be dependent only on G. So K will be dependent only on G, and we're done. So, but before that, I need to show you my face because this is a homework presentation, and I need to let my professor know who I am. So let's do it. Camera. Uh, okay, done. And let's come back here. Wait a sec. Okay, so before proving that, we need to prove a little lemma or Gauss coordinates equations first. So if you can, let's just see the Gauss equation. You can see that on the right-hand side, there is this term. If you set J equal to K equal to 1 and L equal to I equal to 2, then this term becomes H11, H22 minus H12, H21, which happens to be determinant of H. So it's in a two-dimensional manifold, so it's just 2 by 2 matrix. And then you can sort of move the G part to the other side. You multiply by GQL on both sides, and you can see that the left-hand side is the determinant of H, and the right-hand side, I mean, and the left-hand side is only dependent on G because gamma is only dependent on G. There's the 1/2 expansion, right? We'll do it later. So gamma is dependent only on G, so determinant of H will be, okay, we're done then. Let's prove this first. So before proving it, okay, let's prove some claims first. Let's do it first. So we need to evaluate this term first. This is actually by definition equal to partial d partial I partial j, and d has a tangent part and normal part, right? So the tangent part is by definition is the nabla part, and the other part is along the Gauss map. So it's actually equal to this. And in the homework we have proved that dxy nu is actually hxy. So this term is actually hij, right? By nu. And the first term by definition is just gamma. And gamma is defined as coefficients for that. Yeah. So we now have this formula, which are going to be used repeatedly in our proof. Let's do it. And well, our proof is based on the fact that the whole thing is very good, it's smooth, and so the derivatives, you can freely exchange the order of partial derivatives. And let's evaluate this part. I can just evaluate this. And you swap I with K, and then you equate those two different expressions. Then you can see Gauss and Koda's equations emerge. So let's calculate this part first. Oh, sorry. This is equal to, well, we've calculated the inside part first already. So let's just use Leibniz rule and computation. This is the first Leibniz rule. And this is a second derivative of f. So you take partial uk, like partial ul, you get this one, right? It's by definition. Yes. And the second term, hij, partial uk, nu, plus partial nu, partial uk. Nu is like very hard to write. Okay. Okay, we're done. And we can see that there's another second derivative here of f, which can be further substituted by our previous formula. And there's the partial nu, partial uk part, which later we can just expand it. Okay. So let's solve one by one. But the first one is already solved. Let's do this part first. Okay. So we need to calculate partial nu, partial uk. And we know that nu is a unit vector, so it has the fixed length. And we know that the derivative of a fixed length vector, in particular a unit vector, is perpendicular to it. So partial nu, partial uk should be perpendicular to nu, which is the Gauss map. So it should be lying in the tangent space, which is spanned by partial f, partial u, q, say? Okay. So, or ul, I mean, q is ugly. Let's do it. So we can sort of write it as a KL, I believe, partial L, right? We can sort of expand it into something like that. And now we only need to calculate the sort of coefficients for this. And we know that by definition, hij is minus partial nu, partial ui, partial f, partial uj, right? And it's sort of like an inner product. And this one is not an orthonormal basis. You have to keep in mind. But it sort of tells you the information about partial nu, partial ui, how it's expanded on the basis. So let's just do it by plugging in this expression into this term. And we sort of need a rearrangement. Let me do minus sign on the left-hand side. And this part becomes AKL partial L partial J, right? And because it's a bilinear, I mean, it's an inner product. What can you say? Yeah, it's equal to that. And the partial L partial J inner product, by definition, it is equal to GLJ. So let's do GLJ. Okay, very good. So this is equal to minus HIJ. So to calculate AKL, we only need to get GLJ to the other side just by multiplying an inverse to it. So wait a sec. And do I need to erase it? Not really. I think I can just leave it there. This is equal to this, right? Hence, we get this one is equal to, you multiply by the inverse of it, which is denoted by the upper indices, is minus hij uh, well, uh, G L. Am I doing right? Wait. Um. Oh. Um. This is actually okay. So let me fix it because this expression is for k to be here. I'm sorry. So let's do a k here, and this is actually HKJ, right? Yes. Yes, yeah, it's HKJ, and then GLJ. Now J is the dummy variable. Okay, good. Yeah, we're doing good. Therefore, we have partial nu, partial UK equals the minus HK. Let's use another letter for the dummy variable. Let's use Q and then partial L. Ah, we're doing right. Great. So this is a formula for partial nu, partial UK. And we're doing great. Now, this let's just put it in. Plug it in, duplicate a part, this part, and then try to plug it in. Equal to this. And for this part, it becomes gamma Q. Let's use Q, KL partial Q plus HKL nu. Right? This is by our previous formula. And by the formula we just derived, this part is equal to minus HKQ GLQ partial L. Great. Now we can sort of combine everything together. Notice that we have partial L, partial Q, partial L. These are in the tangent space. And these, which are, well, along the Gauss map. So we sort of combine everything together. Tangent space to tangent space. Of the UK. Well, minus this part, which is HIJ, HKQ, DLQ, and do a partial L. And this part, let me write it down first. I know it's a dummy variable, we all know. Partial Q, and there is the gamma. I mean the Gauss map part, which is the gamma Lij HKL plus partial Hij partial UK. Yeah, great, very good. Now, because this part has both L and Q dummy variables, so we take summation basically, and taking summation, so we can actually exchange L and Q because they are all dummy, and we now try to exchange that. Okay, it becomes, well, for the Q becomes L, and A Q L L. Great. Wait, no. Doesn't match. Oh, yeah. Now it matches. Basically, you swap L with Q, and now you sort of match the upper and lower indices. Yeah, good. Now we have this term. Now it can be combined into the previous terms, and we sort of write it down, shall we? Let me do it. Let me do it. Duplicate. Good. Now it's equal to this part, and we erase this. L. Good. Okay. Now this is this one, right? Okay. Which is invariant under the permutation of ij and k. So this would be equal to, if we were to swap I with j, I mean I and k, and this becomes, well, because you can see clearly that this is symmetric with respect to I and j, right? So it doesn't help. But let's swap I and k, and it becomes, oh, I need to write it all down again. K becomes I becomes k becomes Q, oh, I becomes k becomes gamma, L is dummy, I becomes, okay, now we're done, basically, because, well, this and that are all linearly independent. Well, the Gauss map, it's perpendicular to all partial L, right? So it's actually perpendicular to the tangent space. Of course, it's independent, okay, of the tangent space. And inside those are independent as well. So the coefficients should match each other. Now, because the upper thing equate the lower thing, the coefficients should match. So this would be equal to this, and this would be equal to this. Okay. Then we observe a little bit more. Um, okay, we cannot observe anything in particular. Okay, let's just write it down. I thought I could have simplified the calculation, but no, we just write it down. Write it down. UK minus. So I try to move everything to the left-hand side. Move this part and this part. Put these two together. Partial gamma L kj partial ui. And this part with this part, which is plus this part, this part first, which is gamma q ij gamma aq l minus gamma q aj gamma liq. Okay, and this part is left, so you sort of need to move it to the other side, which is actually H I J H K Q G L Q minus, well, it's a swap of I and J, I and K actually, so it's H K J H I Q G L Q. So it's G L Q H I J H K Q minus H K J H I J H. Done. Now you can check. This is actually this one. This is actually the Gauss formula, and we had the Gauss formula here. Very good. Up to a swap of indices, I think. And this part equal to that part, which is the Gauss map coefficient, that would give the Koda's equation. Basically, you move it, yeah, you put them together, you get the Koda's equation. I don't want to do it. Not related to our thing today. Okay, so we have proved the Gauss-Koda's equations. Now we're going to show that G is intrinsic. I mean K is intrinsic. How do I copy this? Yeah, good. So you can see that as we talked about earlier. Well, you put the GQL, you multiply by GQL on both sides, and it's inverse, right? So it's cancelled, and you get this part equal to that part. So you can see that by setting J equal to K equal to 1, L equal to I equal to 2, we have the determinant of H, which is H11, H22 minus H21, H12, is equal to the left-hand side by setting, let's set it. GQ, L is 2, sorry, Q, L is 2. Really? Do I really need to write it down? I don't think so. Well, actually, I don't need to write it down. Okay, so this part are all gamma something, and this is G. Of course, G is dependent on G only. And the gamma part, well, it's famous. Let me do it. Write it down. This is GKL. Partial G IK partial UJ plus partial G JK partial UI minus partial GIJ partial UL. Okay, it's out, sorry. Now, well, by this formula, gamma is dependent only on G. It's actually the definition of gamma in the Riemannian geometry after you sort of introduce manifolds. Yeah. So we're done. Yeah, happy. So actually the whole thing is picked from a list of theorems that I can prove as my homework presentation. And the list of proofs, the list of theorems are, let me do it. These uh, are these. So I just picked the one that I think is the easiest, easiest to prove from the list. And if you are interested, because I'm gonna post it on a public website, If you're interested in any of the theorems other than Gauss' famous theorem Egregium, then you can comment and I will do the proof. Thank you.